In a recent video, you took y equals mx plus b and you learned how to graph it or look at a graph and turn it into y equals mx plus b, but we didn't relate it to any sort of real scenario. So in this video, I'm going to do a short relationship, a short outline of a relationship between this and a worded scenario that you probably worked with before. Okay, so take a moment to go ahead and read this scenario. Pause the video if you need to, because we're going to turn this into math. All right. We've got ourselves a candle, and that candle is burning away, and because it's burning away, it's going to be shrinking. The height is shrinking or reducing at a rate of 2 centimeters per hour. So you can turn this into an equation, and I did it in two different forms. I used the traditional x and y, or I used function notation, but they're the same thing. And basically what's happening here is you have a 30 centimeter candle that's reducing by 2 centimeters per hour. The height of the candle is 30 centimeters and it's reducing by 2 centimeters per hour. Now if you take a look at this, this doesn't necessarily look like it's in y equals mx plus b form, but it's close. And the only thing you would have to do to turn it into y equals mx plus b form is switch the order. This minus 2x can go out in front. This 30 or positive 30 can go behind. Now both of these are valid. Either one works. But if you want to put it in the true y equals mx plus b form, this is the way to do it. This one's going to work just fine for you. But I want to show you something about this equation or this equation using either one. You can go ahead and graph that, and I need to adjust this a bit. Okay. You can go ahead and graph that. Now there's several ways to get that done. One way, you could recognize that this is in y equals mx plus b form, and you could plot your y-intercept, and you could start counting down your slope. Down 2 over 1, down 2 over 1. What you need to notice, though, by the way, is this scale on the x-axis goes by ones, and the scale on the y-axis goes by twos. So you have to keep that in mind when you're counting your slope. So by plotting the y-intercept and the slope, you can get that line. But if you didn't want to do that, or if you weren't comfortable doing that because you didn't like the scale, you could fill out a t-chart, plug in two different values for x, and get out two different values for y. So if I plugged a 0 into here, I would get out a 0 for x, I get out a 30 for y. If I plug in a 10 for x, when I do that math, I end up getting a 10 output for y. So I plotted those 2 points. Plot those 2 points, connect the line, and you have it. But what you need to notice here is the slope of this line, which I computed over here to be -2. That slope also turns out to be part of the problem. Going up there, the candle is shrinking at a rate of 2 centimeters per hour. And it turns out that when we did our graph or our table, the slope was -2, because the slope or the rate of change is always going to have a very, very important role in the problem. And in this case, your y-intercept also has some deep meaning. My y-intercept is 30. Well, 30 has something to do with this problem. And in this case, it's the original height of the candle. So my y-intercept mattered in the problem. My slope mattered in the problem. And if you want to even get more in depth, there's my x-intercept. And that means something in the context of this problem. And that would be, after 15 hours of burning, my candle would now be burnt out or burnt down to a height of 0. So the purpose of this was just to show you that these scenarios which for a while now you've been turning into equations. And whether you knew it or not back then, when you were turning these into equations, you were probably turning them into a y equals mx plus b slope-intercept form equation. And even though you maybe used to be graphing it by data table, you could also graph it by thinking about the y-intercept and the slope.